Hello, I'm Who Are We, and today's episode of The Cutting Edge, we're going to be talking about the primary motor cortex, or M1. It is a fundamental region in the brain responsible for the execution of voluntary movements. Located in the precentral gyrus of the frontal lobe, M1 plays a pivotal role in translating neural commands into precise motor actions via its extensive connections to the spinal cord, brainstem, and other motor-related areas. This lecture will cover anatomy, function, neural circuits, disorders, and contemporary research on M1, including some controversial topics like neuroplasticity, brain-computer interfaces, and free will in movement initiation. So let's start with the anatomy of the primary motor cortex, M1. Location and structural organization. So the M1 is situated in Brodmann area 4 on the precentral gyrus. It lies anterior to the central sulcus, adjacent to the premotor cortex and supplementary motor area, SMA. The region is somatotopically organized in a layout known as the motor homunculus, where different body parts are represented proportionally based on their motor complexity. For example, hands and face have larger cortical representation. Cortical layers and neuronal composition. The fifth layer, layer 5, is dominated by Betz cells, which are giant pyramidal neurons that send motor commands to the spinal cord. Other layers contribute to intercortical communication and sensory integration. Functional roles of the primary motor cortex: execution of voluntary movements. M1 generates motor commands that travel through the corticospinal and corticotubular tracts to activate muscle groups. It is responsible for the force, direction, and speed of movement. Motor learning and adaptation. Although the premotor cortex and cerebellum contribute to learning, M1 retains motor memories through experience-dependent plasticity. Skilled movement, for example, playing an instrument, results in M1 reorganization, otherwise known as neuroplasticity. M1 exhibits plasticity, allowing cortical areas to adapt after injury as well. For example, in stroke rehabilitation, studies show increased representation for frequently used body parts in skilled professionals. For example, the violinist's left hand. Communication with other motor areas. It receives input from the premotor cortex, or PMC, in movement planning, the supplementary motor area, or SMA, in coordination of complex sequences, the basal ganglia in movement initiation and inhibition, the cerebellum in precision and error correction, and it sends outputs to the spinal cord via the corticospinal tract for voluntary muscle activation, and the brainstem via corticotubular tract to control cranial motor functions. Neural circuits of the primary motor cortex: the corticospinal tract, or the pyramidal system. It's a direct pathway from M1 to the spinal cord. It's essential for fine motor control, especially of distal limbs. Damage can result in spastic paralysis. The corticotubular tract, which is M1 projections that can control cranial motor functions, for example, facial and speech muscles. We also have the basal ganglia and cerebellar loops, which are indirect modulation of movement, precision, and initiation. Disorders associated with M1 dysfunction: stroke and motor deficits. Ischemic strokes affecting M1 result in contralateral motor weakness or hemiparesis. Neuroplasticity and rehabilitation are key to functional recovery. Amyotrophic lateral sclerosis, or ALS. It affects upper motor neurons in M1, leading to progressive muscle weakness. And motor neuron diseases and paralysis. Damage to corticospinal neurons in M1 can cause spasticity or loss of voluntary movement. Contemporary and controversial research. Neuroplasticity and motor cortex rewiring. Contrary to traditional views, M1 is not purely an execution center. It adapts to injuries through cortical reorganization. The controversy is M1 capable of taking over other cognitive functions post-injury. We also have brain-computer interfaces, or BCIs, and motor control. M1 neural activity can be decoded to control robotic limbs and prosthetics. Experiments with direct cortical stimulation allow paralyzed individuals to regain movement. Should BCI enhancements be used in healthy individuals for augmenting motor performance? And again, this will connect to what Neuralink is doing. And you also have a lot on David Eagleman. I believe he delivered a TED talk about this, actually. It was somewhat interesting, and of course, I personally didn't actually like his main book, The Brain, The Story of You, but I think he does go into it in, I think it was chapter 6 from what I recall. But yeah, those are some places if you want to dive deeper into it. But there's lots that's progressed since he delivered those things, and it's a very interesting field, of course. So, free will and movement initiation. Neuroscientific experiments, such as Libet studies, suggest that unconscious brain activity precedes conscious movement decisions. M1 has been implicated in voluntary action, but the debate over free will versus pre-programmed neural activity continues. If movements are initiated subconsciously, how much control do we really have over our own actions? M1 stimulation in enhancing athletic performance. Some controversial studies suggest transcranial direct current stimulation, or TDCS, can enhance M1 function, leading to improved reaction times and strengths. Ethical concerns arise regarding neural doping in competitive sports. Conclusion. The primary motor cortex, M1, is central to voluntary movement control, integrating sensory and cognitive inputs to execute precise motor actions. While traditionally seen as a motor output center, modern research highlights its adaptability, plasticity, and its role in advanced motor functions. Key takeaways. M1 controls voluntary movement via corticospinal and corticobular pathways. It undergoes neuroplasticity, adapting to injuries and training. Modern BCIs have successfully interfaced with M1 to restore movement in paralyzed individuals. Free will and movement initiation remain debated topics in neuroscience. Neuromodulation techniques raise ethical concerns about motor enhancements in sports and cognitive augmentation. Discussion questions. To what extent can neuroplasticity in M1 compensate for motor impairments? Should brain-computer interfaces be used for motor augmentation beyond medical necessity? And does the research on M1 and free will challenge our understanding of personal agency? Now, those are, of course, interesting questions. But I believe most scientific people take the deterministic route for most things, other than obviously quantum physics, which is a big question there about the validity of whether or not. I mean, you have concepts like string theory, but we also have the brain-computer interfaces. And beyond medical necessity is almost a bad heuristic, because what is medical necessity? I mean, if we look at the DSM, the rigor is 0.4, and we're, theoretically we would classify that as a medical necessity, as we give people a lot of very neurotoxic drugs and just toxic for the body. They often harm the liver and the kidney specifically, along with, obviously the heart, not to mention the brain. But, beyond medical necessity is a hard thing to say and to define. So I think that's going to be a major issue that we're going to have to deal with really, really soon. So anyways, this concludes our lecture on the primary motor cortex, M1, and thank you. Again, the Libet studies are quite interesting if you do want to look into that. You have the David Eagleman stuff, you have all the Neuralink stuff, which is worth going into. There's a lot of pages that a lot of the employees at Neuralink run. So, and they have some interesting content up there. So, anyways, I hope you enjoyed. Thank you.